All right, so appreciate you sticking around this long, my precious, precious darlings, in order to talk about the next section of Organic Chemistry 2, which is aromatic compounds. And so it starts off with a discussion about benzene, and just like every other chapter in this course, it's going to talk about nomenclature. And so if you think about the priorities of different groups, you won't be surprised to know that when we name benzenes that have certain substituents on it, even said N and wrote an M, benzene. If I put a chlorine here, then this would be chlorobenzene. Same thing with nitrobenzene. And it turns out that for every group other than a methyl group, we will just use the regular sort of IUPAC nomenclature rules. And so this would be an example of ethyl benzene. Now remember, if there's a chain and the chain is longer than 6 carbons, then it becomes a phenyl substituent. And so that's not the case here, but it could still be a phenyl substituent, just like we showed you guys back in Organic Chemistry 1. However, it turns out that there are quite a few common monosubstituted benzenes that actually just have common names. And this is the one time when I'm really going to get excited about common names. Usually at this point, you have figured out that I love IUPAC nomenclature for the fact that it's so systematic, and you can rely on that system. We don't have to rely on memorizing common names. But when it comes to the benzene derivatives, I'm pretty excited about the common names. This is a little bit of a going out in left field for me. I don't know what the word was I was looking for. And so what I'm going to do is I'm going to show you these common monosubstituted benzenes and give you their names. And your job will be to, you're muted so you can't say this, memorize them, right? So these are the ones you have to memorize, and you have to know their names. So when you see these on the next exam, whether it's name to structure or structure to name, you'll have to be able to reproduce it. And so that's the methyl group on a benzene, that's toluene. A methyl ether on the benzene is anisole. A OH group on the benzene, you guys should know this one, phenol. What are some of the other functional groups that we have in organic chemistry? What about the amine? That would be aniline. And oh, let me look it up. Is that an A? Should it be ANA or ANI? Man, if I had a visual memory, I would know. Just want to double check. Come on, man. Nobody's beat me to it in text messages yet? It's an I. Look at that. I had it right. Spent some time thinking about it. Okay. Another functional group we could have could be a carboxylic acid. This is benzoic acid. Another functional group that we could have is an aldehyde. Guess what that's called? Benzaldehyde. This one's interesting. Styrene. You ever heard of polystyrene? Think back to the polymerization reactions that we discussed in Organic Chemistry 1. If you were going to make polystyrene, this is what you would make it from. And the last one that you have to know is acetophenone. Okay. Any questions about that? Any questions about that group? So just pause for a quick beat. All right. What about this one? What about di-substituted benzenes? Let's do this one. There's two versions you could say with this one. This one could be 1,2-dimethyl benzene. Nothing wrong with that. Or it could be 2-methyl toluene. It could be 2-methyl toluene. Although there's something else that's really interesting about di-substituted benzenes. And let's use the toluene as an example. When it comes to benzene, there is this really unique naming system. And it has to do with the positions that are around a benzene and it's based on how far away they are from another substituent. So this works essentially only with di-substituted benzenes or with a benzene that has a common name, as in toluene. And so if I were to think about these different positions, they have names. This is the ortho position, and so that means that so is this. And that what that implies is that the position that is one space away from the substituent that we're referring to is the ortho position. Same thing with this one. They're identical. They're two spaces away. It's meta. And the last one, there's only one position. It's called the para position. So what else could we have named this toluene? We could have called it, instead of using a number to identify the location of this other methyl group, we could have just said that it's ortho methyl toluene, and even we just shorten that to O. And so you do have to somewhat become familiar with the ortho, meta, para designations, because as we start to talk about more advanced reactions of benzene, particularly with electrophilic aromatic substitution, we'll see that we'll have to use these words to quickly refer to different positions where this substitution can happen. Well, the short answer is is yes. It really is only for di-substituted benzenes. So once we have 3 substituents, then we have to kind of go back to a standard numbering system. And so let's do an example real quick of what I mean by that. What if you had what is this thing called? What is this thing called? No, and it's not with methyls only, right? And so I could do this, and this would be orthobromo. And we'll talk about the parent name in a second. If I were to take the bromine off and put it over here, this would be metabromo. And if I were to take the bromine off and put it over here, this would be parabromo. And so it really is about the common name. And so what this ortho meta para designation works essentially exclusively with those benzene monosubstituted benzenes that have common names. So in this case, we would call this para bromo anisole. But once I put a bromine at another position, and I want to get rid of some of this stuff, so make it a little cleaner. Then we really can't use that anymore. And we have to sort of go right back to our normal numbering scheme. And the only thing to kind of point out is that, of course, then the parent group gets the first number. And so since this is anisole, that oxygen connection is the first connection. And then we would number the ring the same way, in the way that gets us 1, 2, 3, 4, 5, that gets us the lowest set of numbers. So this would be 2, 5, dibromo anisole. Okay. Let's name this one. What would this one be called? This might be the best hexagon I've ever drawn. So let's do this. Let's think about this. What's this parent group? What's the parent group that involves this guy? What's it called? Take a quick second, type that in chat. This is some sort of toluene, right? This is some sort of toluene. And so what do we got going on here? We've got a group here, a group here, and a group here. It doesn't matter which direction we number it. It's the same either way. So what do we get? We get 1, 3, 5, trinitro toluene. Any questions about how to name this compound? This trinitrotoluene, this T Yeah. Boom. Boom, there it is. So take a quick break. I'm going to give you about 30 seconds. Draw this one in your notes. 2,6-dibromo 4 fluorobenzaldehyde. So, oh my goodness, did I do that? Jeez, let's start over. Let's start over. Yep, absolutely. Let's come back here. So the comment was made that I numbered this TNT incorrectly. And that's absolutely 100% true. I didn't number it correctly. So let's go right back to it. And look at that, not NO3, NO2, NO2, NO2. This is, in fact, number 1. Right, this is number 2. This is number 4. This is number 6. So it's not 1, 3, 5. It's 2, 4, 6 trinitro toluene. Good catch. Yeah. So take a moment. Now that you've had a good laugh at me, I love good comedy. Draw out this structure. I'll do the hard part for you. I've deciphered that part of the structure looks like this. And it's benzaldehyde, so that's part of it as well. And so if it's dibromo 2,6, there's 1, there's 2. There's 6. And the other one was 4. Fluoro. Okay, any questions about that? Okay, recall that benzene actually exists in 2 different resonance forms. And we can even use a mechanism to show the movement of the electrons from one resonance structure to another. And so that means that if we were to draw the resonance hybrid, we would have a partial bond in each location. So what should you expect about the bond lengths of all the carbon-carbon bonds in benzene? Hopefully you're saying that they should be all equivalent. They should be all the same. And in fact, they are. And oftentimes, I know you've seen me, you'll see this drawn as a representation of benzene. And the reason we do that is because it's nice and easy. It's quick to draw a little circle to show the resonance, to give you kind of an idea about this is the resonance hybrid of benzene. But what we will do is we will use these, because when we do mechanisms, you know, we want to make sure that we're keeping careful track of the electrons. And so we can't really show electron movements with this type of resonance hybrid. So, but you will see it commonly used not only in my lectures, but certainly on other videos in other places when keeping track of those electrons aren't so crucial. All right. So what we know about, one of the things we know about benzene is that it's unusually stable. And remember what I mean by something that's stable. If I'm talking about something B that's more stable than A, that means it's lower energy on a free energy graph. And so if I'm thinking about a combustion analysis or a hydrogenation analysis, the more stable species would have the smaller energy of hydrogenation, and the less stable species would have the larger energy of hydrogenation. And so one of the things that we use to talk about how we know that benzene is particularly stable is we use this hydrogenation reaction. If I take H2 and platinum with cyclohexene and turn it into cyclohexane, the energy of that reaction is on the order of 120 kilojoules exothermic. So if I were to say, okay, what am I going to do with, if I want to do that same reaction with three double bonds, then I should get 3 times negative 120 kilojoules per mole. So we might expect that it's 360 kilojoules per mole exothermic. It isn't easy to do a hydrogenation reaction with benzene, but it can be done. This is a reaction that I would put on the reaction board. So it requires 3 equivalents of H2, some sort of metal catalyst, but very high pressure and exceptionally high temperature. We can get that structure to be reduced, but we find that the delta H isn't 360, it's minus 280. So it's about 80 kilojoules per mole more stable than we would expect just from examining the hydrogenation of cyclohexene. So we can talk about where this stabilization comes from if we were to think about it from a molecular orbital perspective. And so if I'm not actually going to do this because I'm going to embarrass myself, but remember, if I take 6 orbitals in, I'll get 6 orbitals out. And because of symmetry, you'll see that the orbital diagram looks like this. And what I'm not going to attempt to draw is the actual picture of the orbitals. What I want to do for a moment is stop there and switch my share. And show you this picture of what I'm talking about. And the reason why I'm not going to draw them is because it's just very difficult to draw this particular set of molecular orbitals, because I'm a terrible artist at the end of the day. That's really all that's going on here. But if you look at the ground state, the very lowest energy orbital, this is the version where you would have all of the p orbitals lined up in the same phase. The reason why there's a degenerate set of orbitals in the situation where there's only one node is because you can have one node essentially along the XY axis and another node along another axis. So perpendicular, you can have these 2 nodes perpendicular. So in this case, because there's 2 versions, you end up with a degenerate set of orbitals. And so the same thing occurs when you have 2 nodes. You can have 2 nodes this way or 2 nodes that way, in which case you're going to get another degenerate set. Then the highest energy orbital is the orbital where all of the p orbitals are arranged in different phases and none of them overlap. Where the stability comes from is that if we were to think about the relative energy of all of the different p orbitals, so these are atomic p orbitals, each one having a single electron in it, we fill up the electrons and all 6 of them are in a lower energy state. And so this is a molecular orbital version of where this stability comes from. And we're just going to kind of leave it there. That's one thing we can show you that says this is why it's more stable. We'll use molecular orbital theory and mix up these p orbitals from an atomic perspective and do a linear combination of atomic orbitals to form molecular orbitals. And now we can say that the sum total of these 6 unmixed atomic orbitals is higher than the new molecular orbitals that we form. And since the occupancy of those orbitals is lower in energy, it's more stable. There's going to be some more things that we want to talk about when it comes to molecular orbital theory, but it's really going to rely on geometric shapes and symmetry arguments, and we'll look at those later. They're called Frost circles. And so what we want to do now is consider a couple of other molecules. What about this one and this one? Just like benzene, they have they have an alternating set of double bonds. They're conjugated. Are these more stable? Well, remember that it's very difficult to react with something that is stable. And in fact, if you try to react Br2 with benzene, you get no reaction. But if I react this 8-membered ring with the same situation of alternating double bonds with bromine, we do get a reaction. We get exactly the reaction we would expect. I don't like that at all. There we go. We get this. What about the square? Is that more stable? It's in fact so unstable that it reacts with itself quite quickly. Let me show it actually a different way. This is a Diels-Alder reaction, and it creates a high energy intermediate that quickly rearranges to form another conjugated system of double bonds, and it immediately forms this guy. So we're back to where we started with this 8-membered ring with alternating double bonds that we also know then is reactive. So there's something going on here. It's not just about the fact that there's alternating double bonds. That's not what's leading to the in and of itself to its stability. And so what we get to is we get to this idea that there's only particular situations that involve aromatic compounds. And when I say aromatic, I mean that they have this increased stability. And we get to this idea that we have this rule, and it's called Huckel's rule. And Huckel's rule helps us predict when we might see some aromatic stability from a set of pi electrons. And the rule is 4n plus 2, where n equals 0, 1, 2, 3, so on and so forth. And so if we just quickly write down and these are the total number of pi electrons. So if you have 4n plus 2 pi electrons, you might expect that the species that we're looking at can show this aromatic stability. And so what does that mean? So if I take 4 times 0, add it to 2, I get 2. If I take 4 plus times 1, I get 4, I add 2. There's my benzene, six electrons. What about 4 times 2 plus 2, that's 8 plus 2, that's 10. 4 times 3 plus 2, what do I get there? 12 plus 2, I get 14. And so what do I get? 1 pair, 3 pair, 5 pair, and 7 pair of pi electrons. So if I go back to this structure and I go to this structure, I see that I only have 2 pair for 8 pi electrons, and here I have 4 pair for, oh, I did that wrong. 4 pi electrons here, 4 pair for 8 pi electrons. So this is Huckel's rule telling us that these things will not exhibit any of that aromatic stability. And of course, we know that from their reactivities because they react much more readily than does the benzene. All right, and so that's where, look, we can take a, it turns out that with molecular orbital theory, we're invoking symmetry. And because of this symmetry, there is this interesting feature that if I'm really good at drawing, I can take a circle. Let me actually expand this out. I can take a circle, and if I want to consider any ringed structure with a set of conjugated double bonds, then I can put that ringed structure in this circle with one of the points coming down. And each time the shape of the structure strikes the circle, that is the molecular orbital diagram for that particular molecule. Make it a little bit more pretty. What's difficult is to remember that if you're a really good artist, and this is a perfect circle and a perfect square, that's exactly halfway between, and that just like before, you have bonding orbitals and anti-bonding orbitals. These orbitals that fall directly on the line are called non-bonding orbitals. And so if we were to populate the 4 electrons in these orbitals, we would see that we have 2 electrons that come into the non-bonding orbital. And in this case, we would say that the structure is anti-aromatic. So let me just show you a couple of more examples of these frost circles. When we can do a pentagon. If I were going to do a pentagon, I would do this. So I would have and so this is sort of the dividing line there. Again, if you're not good at drawing, it's easy to mess up where that halfway point is. And so in here you have 3 bonding orbitals. And 2 anti-bonding orbitals. And in this case, there are no non-bonding orbitals. One more example. Let's go take a look at that 8-membered ring. Let's see if we can draw a frost circle for that 8-membered ring. So remember, we need to put it on its tip. So that means the 8-membered ring would look like this. So I'd go 1, 2, 3. Let's try to back this up. It's much more difficult than 1, 2, 3, 4. These should be essentially in the middle. There it goes. That's better. Yeah. 1, 2, 3, 4, 5, 6, 7, 8. And it turns out that the middle is actually here. And so you get 1, 2, 3, 4, 5. That is the middle. I'm sorry. One, 2, 3, 4, 5, 6, 7, 8. So 3 bonding, 3 non-bonding, and 2 or 3 anti-bonding, and 2 non-bonding. And so putting the 1, 2, 3, 4, 5, 6, 7, 8 electrons from that conjugated system, you get 2 non-bonding electrons. You always have to orient. The question is asked, how do you know how to orient the cyclic compound? And the answer is you always have to start with a point down. So you start with a point down. And so if it's like a diamond, or in other words, a square, then you rotate it so it's like a diamond. If you have the octagon, which is much easier to draw with the flat parts being down, you have to rotate it so that this point is down at the bottom of the circle. So with both the square version and the octagon version, you would predict that they are anti-aromatic and thus very unstable as molecules themselves. But what we say is that a molecule will avoid being unstable and thus will avoid being anti-aromatic and thus unstable by distorting itself so that the pi orbitals or the p orbitals are not overlapping. And so in other words, what we say is this would be the situation with the Frost circles would be if those p orbitals are perfectly overlapping. But if we end up in a situation that one of the molecules is anti-aromatic, then what they do is they just distort themselves into a different shape, and then all of a sudden these molecular orbitals don't apply anymore, and now they go from anti-aromatic to just non-aromatic at that point. And so it's a little bit of hand waving, but that's exactly what the textbooks do, is they talk about the shape being distorted. And in fact, it's actually true from experimental point of view. The 8-membered ring actually ends up being sort of a boat of a thing. Did I do 8? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. Didn't draw it correctly. So I need to, here we go. Then you get your alternating double bonds like this. And so that 8-membered ring stops being flat, it becomes a boat. And because it becomes a boat, the p orbitals no longer are consistently overlapping. And so this molecular orbital diagram no longer applies to the actual structure. It's some other molecular orbital diagram. And so we don't we know that this 8-membered ring exists. It isn't particular, it is reactive, but it's not so highly reactive that we can't isolate it. So it really isn't flat, and we know that it's not flat from experiment. So it has some other sort of shape. And so this brings us to, not only is Huckel's number important when it comes to predicting aromatic compounds, but it also has to be a ring of continuous overlapping p orbitals. And on top of that, you have to have a Huckel number of pi electrons. Both of these conditions have to be met in order to have an aromatic compound. So the question is asked, the non-bonding orbitals is what makes the compound anti-aromatic with frost circles. And to be specific, it's not the fact that they exist, it's the fact that there are electrons populating those orbitals. That's why it's anti-aromatic. So a molecule will not stand to be anti-aromatic. So it'll do something like change its shape or give up some electrons or gain some electrons in order to stop being anti-aromatic. So let's examine this. The question is asked, these two conditions have to be met in order for the compound to be considered aromatic? Question. Absolutely. That's exactly what we're saying. And so if we take a look at the molecule that I just drew, it's a conjugated system of overlapping p orbitals. It's a Huckel number of electrons, but what is it missing? It's not in a ring. So they're overlapping, but they're not in a ring. And so even though it's a Huckel number, it's not aromatic. If I take a look at this molecule, what am I missing here? Well, first of all, I've only got 4 pi electrons. That's not a Huckel number, but I've also got an sp3 hybridized carbon here. And so if I have an sp3 hybridized carbon, then both of the hydrogens in this molecule are in sp3 hybridized orbitals. And so there is not an unhybridized p orbital to participate in a continuous overlapping ring. What about this guy? So what did we say about this one? What's actually the problem with this one then? It's not well, first of all, it doesn't have a Huckel number, so that automatically throws it out. And then we know that it's distorted its shape, so now it's not planar, and so it's not a ring of continuously overlapping p orbitals. So in order for this to be true, it has to be planar. So once we get into benzene, the class of compounds that are like benzene are called annulenes. And so benzene is that first aromatic structure. The 6 refers to the number of pi electrons. Well, the next one, this one is 10 annulene. That is a Huckel number. Seems like things are nice and overlapping, but let's blow this up actually right here. Let's take a look at this. Let's blow this up. And let's look at it. We've got a double bond here and a double bond here. What happens? What's going on here? There's some steric hindrance in 10 annulene. And so actually what happens because of this steric hindrance between these two hydrogens is that the molecule distorts, and what seems like a continuous planar set of unhybridized p orbitals actually stops being so. And so it turns out that that structure isn't aromatic. And it's really not until you get up to 18 aniline that it becomes aromatic. Now that I've got enough room in my molecule in order for there to be limited amounts of steric hindrance, thus leading to the planarity that is the requirement for the molecule to be aromatic. Well, so let's do this then. Let's talk about a molecule like this. Let's go back to this frost circle. Let's try to draw this better. So this means I have an electron diagram that looks like this. These are molecular orbital diagram. These are bonding. These are anti-bonding. There's no non-bonding. And we talked about this structure before. We said, why is this aromatic? And we said, oh, well, look, there's an sp3 hybridized carbon there. What did he say about 18 aniline? 18 aniline is the first of the anilines that has enough room to avoid steric hindrance, that it doesn't distort itself, so it stays aromatic. When we do 10 aniline, and I guess what would the next one be? It would be 14 aniline. There's not enough room for those hydrogens not to interact through, and they have that steric hindrance, and so they distort and become unplanar. So 18 aniline is the first one. So let me ask you this question then, back to this cyclic 5-membered ring. Does that mean that a cyclic 5-membered ring can never be aromatic? Well, if I take a look at this guy with just the 2 double bonds, I have 2 problems for my aromatic criteria. It's not a Huckel number, and because of the sp3 hybridized carbon, it's not a continuous ring of planar overlapping p orbitals. But what about this molecule? What about this one? Is this one aromatic? One of the things that you're going to have to be able to do is look at a molecule and tell me whether or not it's aromatic. And so this is the first example of something that's just a little bit less straightforward than one of the other examples. What do we have here? How many electrons in this system? Well, I've got 1, 2, 3, 4 in the double bonds. We got 4 from the double bonds. But I also have 2 from the lone pair. So that's a Huckel number as long as they're actually in a pi system of overlapping p orbitals. Well, let's take a look. What would the hybridization of this be? In order for it to be a negatively charged carbon with a lone pair and not violate the octet rule, that means that there can be only one other bond besides the lone pair, and that's going to be a hydrogen. And so if I am in that situation, then this means that it could be sp2 hybridized. It's technically sp3 hybridized. So let's draw out what we're talking about here. Here is a negatively charged carbon. And so if it could be aromatic if it were to be sp2 hybridized. from our first principles, from what we learned about in Organic Chemistry 1, we would still say, look, this is sp3 hybridized. There's a carbon chain here. I'm just going to put an R there. There's an R group there. I have an hydrogen and I have a lone pair. So that's 4 geometry groups. So that's sp3 hybridized. Well, what we're going to learn about is that if a molecule can gain some stability by having an otherwise sp3 atom rehybridize into sp2, then it'll do that in order to gain aromatic stability. And so what actually happens, instead of this carbon being perfectly sp3 hybridized with an R group here, an R group here, a hydrogen there, and the lone pair there, what happens is that it rehybridizes. It rehybridizes to form an sp2 hybridized carbon, so that I have a p orbital that remains unhybridized where those electrons reside, with quotation marks. And so because it has rehybridized to sp2, I now have 6 pi electrons, which is a Huckel number. And because it rehybridized at this location, I now have a continuous overlapping set of unhybridized p orbitals that can participate in this resonance. And so that, combined with the fact that it's a Huckel number, means that this cyclic 5-membered ring that is an anion is aromatic. Well, what about the situation where it's not an anion? What about a cation? Can a cation do it? Well, let's take a look at cyclopentene or cyclopropene. Cyclopropene has 2 pi electrons. Yep, that's a Huckel number. If it's neutral, then this is an sp3 hybridized carbon. Well, what happens if I lose a hydrogen and I form a cation? What do we know about cations? Cations are sp2 hybridized. So now we get into this same situation. I have a carbon that is positively charged, and I have a set of unhybridized p orbitals that exist in a ring, and there are, because of the double bond, 2 pi electrons. So this structure is aromatic. All right. We're almost there. We're almost done for the day. Let me take a look at situation where we have this guy. You know it, you love it, it's in lots of your reactions, it's your friend and mine. I think that's INE, right? Pyridine. Spelling it completely wrong. Is pyridine aromatic? Yes or no? Think about this. It's got 1, 2, 3 double bonds. So it seems like it could have 6 pi electrons, but what about that one? What's going on there? What's the hybridization of this nitrogen? We know that it's sp2 based on our first principles, based on what we learned in Organic Chemistry 1. So if we look at that nitrogen that's sp2 hybridized, we know that we've got a double bond that goes this way, a single bond that goes that way. If it's sp2 hybridized, it's got a p orbital this way, and the electrons that are in the lone pair are in, these electrons are in the sp2 hybridized orbital. So what does that mean? It's orthogonal to the p orbital. And in this case, we're just going to switch it up to say perpendicular. And so the way that I describe it in this case is to say this lone pair of electrons is stuck out of the ring. It's perpendicular to the unhybridized p orbital. So it's not participating in the ring of pi electrons. Again, I say it's stuck out. And because it's stuck out, I still end up with 1, 2, 3, 4, 5, 6 pi electrons with this overlapping set of unhybridized p orbitals in a planar ring. And so pyridine is aromatic. Well, remember that pyridine is a base. It's a base, a common base, and we use it in a lot of reactions. So what happens if it functions as a base and it becomes protonated? Is this structure, is the protonated version of pyridine with a cation, is it aromatic? Is it aromatic? Let's take another look. Remember, I'm going to have the double bond going out this way, the single bond going out this way. It's still sp2 hybridized. The hydrogen bond is in the hybrid orbital. I still have 6 pi electrons. It's still an overlapping set of unhybridized p orbitals in a ring. And so it too is aromatic. And so what I'm going to do is I'm going to do one more example because I want to show you another case that you might want to consider whether or not it's aromatic. What about this guy? Is this aromatic? Well, remember, at first glance, you're saying this is sp3 hybridized, which means that the oxygen has 2 lone pairs in sp3 hybridized orbitals. But what can we, and it has 4 pi electrons. But what did we say before? If the thing could rehybridize to gain some aromaticity, then it will. And since it has 4 pi electrons in double bonds, then one of the lone pairs can participate in this rehybridized system, and so it will. And so is this aromatic? Yeah. It is aromatic. And it's aromatic because if it can rehybridize to form a Huckel number of electrons